Hello there, and welcome to our last lesson in grade 9 chemistry, which is about molecules. Molecules are substances that are made of little groups of atoms held together. You might know a few of them, like water and carbon dioxide, and even know their formulas. H2O is a pretty common one for people to know, as is CO2. And here we have my son blowing some bubbles that contain CO2 and through a glass of H2O. So a couple molecules interacting right there. Molecules can also be represented using these little model kits that you might have seen before or even gotten to use. And so the molecules will have different structures that represent the atoms inside the molecule. So H2O will have an O that's represented by a red ball there, and two H's represented by the white balls, and that will give you a representation of this molecule. And the CO2, the same thing here. We've got a carbon in the middle here. It's the black one and two of these red oxygens. So that's CO2, and that's another molecule. So we're going to learn a little bit about how molecules are held together, what these little plastic connector thingies represent, and then some common molecules and how we can draw and name them. So molecules are everywhere. Substances all around your home. They can be gases, they can be liquids. The gas that's used here to heat up stuff on your stove is methane, and it has one carbon and four of these hydrogens all bonded together. There's all sorts of molecules inside of living things. You and I are made up of all different types of molecules, lots of different proteins and carbohydrates and fats and DNA, and that is all in the same category of molecules, being those little units of elements being held together. They can be liquids, like in this vinegar bottle. So down here, this is acetic acid, which is the molecule that makes vinegar. And also, of course, as solids, you've got this hand broom here. All our plastics are all molecules. This plastic bench, this plastic bottle. Basically, anything that's plastic is a collection of molecules. So what makes molecules molecules is the way in which they're bonded. This time, instead of ionic bonds, it's called covalent bonds. So we're going to learn a little bit more about those as we go along. So first off, how can you tell if something is a molecule versus an ionic compound? Well, remember the ionic compounds made these lattice work, and they were always a repeating pattern of ions, right? Sodium and chlorine, oppositely charged ions. Now, the one of those ions always had to be a positively charged one, and most often those are going to be metals. So if you see a metal, you can tell right away that it's ionic. If you don't see a metal, that means it's going to be in the other group, the molecular compounds. So let's have a look at a few of these. Here we have sodium bicarbonate. That's the sodium. That's a metal. So that makes this ionic. Got some oxygen. No metals there. That's a molecule. CH4. None of those are metals, so that's ionic. N2. This is does not contain a metal, so this is going to be molecular. Water, there aren't any metals there, so that's a molecule as well. Calcium sulfate, calcium is a metal, so that's ionic. Sodium chloride, the sodium is a metal, so that's ionic. And H3, no metals there, so that's molecular. So you can tell if it's molecular if you can't find a metal. Okay, so covalent bonds is how all of our molecules are going to be held together. And so we got to address what that is, covalent bond. So I kind of like just looking at the name and pulling it apart. The co part means shared and like cooperative. And valent, that's the valence electrons, those outer shell electrons. So instead of those outer electrons only being with one atom, when you make a covalent bond, those electrons are shared between two atoms, right? So you can start off with the hydrogens here. You got two valence electrons. These are individual hydrogen atoms. And then when they bond together, this here will now be a covalent bond because they are sharing their valence electrons as one orbital that holds them both together. So you can think of this as two negatively charged electrons whizzing around two different nuclei, and since these nuclei are positive, they're going to be both attracted to these shared electrons, and that will hold them together. It's a very strong bond. All right, so in order to make covalent bonds, we have to have free electrons that are available for bonding. And so we call those ones the single ones that aren't paired up yet in the basic structure of the atom. So you can tell how many valence electrons there are and then how many free ones are available by drawing the Lewis symbol. If you recall, the column tells you how many valence electrons there are. So in this first column there's 1, the second is 2, we skip this middle section, 3, 4, 5, 6, 7, and from neon down it's 8. And so from there we can actually narrow this down because we're only going to be using nonmetals, so it's only the hydrogen with its 1, and then this small section over here to worry about as far as making molecules goes. So what we can do is look at how many free electrons there are just by making the Lewis symbol, and we can tell how many covalent bonds we can make. So with carbon, if you recall, we put the electrons on to the compass points first before we double up. You see that carbon has 4 single electrons, so that means carbon can make 4 covalent bonds. Nitrogen has 5 valence electrons, and since those two are doubled up, this means that nitrogen can make 3 covalent bonds with the free electrons that it has. With oxygen, again, the ones that are paired up are not available for bonding, so only this guy and this guy can be used for bonding, so that means only 2. And then for fluorine and the other halogens, you can see that there's only 1 that's available for bonding. And so those single electrons, those are ones that we're going to use in order to make bonds and make our molecules. There are a bunch of elements on our periodic table that are molecules all by themselves. They don't even have to interact with other atoms to do so. And so it's good to get to know these ones because you'll see them over and over again in your journey as a student. And so we'll want to get to know them right away. So these are called diatomic elements, and surprise, surprise, di means 2. That means they're going to come in pairs. Now there's a little mnemonic to help you remember, and the mnemonic goes Hofbrinkel, right? So if you remember Hofbrinkel, all of those elements come in pairs and they are bonded together by covalent bonds. So it's H2, O2, F2, Br2, I2, N2, and Cl2. You'll never find those elements all on their own. They'll either be in pairs or they'll be bonded to something else. Alrighty, so drawing molecules is a bit of a challenge when you're learning, so I'm going to show you a few techniques, and you can go through the process of getting to know the methods that work best for you. So there are a bunch of ways to show molecules and the atoms that make them up being held together by covalent bonds. A good starter method is to write out the Lewis symbols, and like so. There's oxygen. We're going to do water here, and then show the atoms that are bonded together by circling the 2 electrons that are going to be shared. So remember, it's only single electrons that can be shared. And so for water, each hydrogen has 1 to share, that oxygen has 2 to share. And so once you've got all the single electrons shared up, that means that you have completed the molecule. All the elements will have full valence shells by sharing rather than transferring electrons. And that means that the molecule will be stable. So oxygen normally has 6 valence electrons, but now it's sharing this guy and this guy, so now it's up to 8. 8 is a nice full shell. That's great for oxygen. Hydrogen has 1 valence electron usually, but if it shares this one from oxygen and this one as well, both of those hydrogens then end up with 2, which is a nice full shell for hydrogen. The other way of showing molecules that we're going to use this year is to use sticks to represent those bonds. And so I would recommend that you start and practice using this until you get confident with it. And then you can move on to a little quicker method where instead of drawing the two electrons and circling them, you can just draw a line to represent the covalent bonds. They mean the same thing. It's just a little more efficient once you get used to how many bonds different atoms can make, and you can more quickly and a little more cleanly represent the molecule. So this here is a covalent bond. It's one method, but this stick also represents the same thing, covalent bond. Okay, so I'm going to show this method to start with most of the molecules I'm going to demonstrate, and then second I'll demonstrate what it'll look like once you're able to move on to this, or the next level, which is to use the sticks for the bonds. Alrighty, so bonding your atoms together to make molecules with covalent bonds is a little trickier than with the ionic compounds because there are multiple ways in which these atoms can bond with each other. So we're going to use those Hofbrinkel elements to illustrate this. So if we want to make chlorine, the Hofbrinkel chlorine, which is Cl2, what we'll do is we'll put a chlorine here, and we'll put 1, 2, 3, 4, 5, 6, 7, and then we'll put another chlorine here. Now it also has 7, but when I'm going to put my 7th one down, I'm going to put it on this side so that the two single electrons are facing each other. That way I can show the bond a little more easily rather than have to make some weird curly thing that goes around the atoms. So that's a way to show chlorine bonded to each other. We call that a single bond because there's only one pair of electrons being shared. Single bond. Drawing it with sticks, of course, it would look like, 1, 2, 3, 4, 5, 6, 7, and we could just draw a stick, go over to the next chlorine, and complete it that way. So that's the equivalent. Oxygen. So if we do oxygen, it's got 1, 2, 3, 4, 5, and then since I want to make bonds, I'm going to put the 6th one over here. You can move them around however you like, as long as you're putting them on the 4 sides, and arrange the single electrons to be as close as possible to each other. The other oxygen we'll put next to it, 1, 2, 3, 4, and then we'll put 5 and 6 like this. And so now the single ones are next to each other, and we can make the bonds that way. With the stick diagrams, draw your two lines right next to each other to represent the two bonds that happen. Since there's two pairs of electrons being shared here, we call this a double bond. Double bond, right? So single bond, 1 electron pair being shared, and double bond, 2 pairs being shared. Now, surprise, surprise, nitrogen has 5 valence electrons. I'm going to put the 5th one on the far side there, and then the other one will put its 5th one on the right. So that means we can make a bond here, and a bond here, and a bond here. And that is a triple bond. 1, 2, 3. Very strong bond. A lot of explosives end up producing nitrogen, and since nitrogen is so low energy and stable, the difference between the explosive that you start with and the nitrogen, which is low energy and stable, that difference in energy is what's given off, and that's what makes it makes the explosive so powerful. So for a triple bond, you use 3 lines. You can show the 2 like that, and then put the extra valence electrons on the far side away from them like that. Okay, so those are 3 options with bonding. Single, double, and triple. There's no such thing as a quadruple bond, so you don't have to worry about that. And you'll use any combination of these in order to make up the molecules that we're going to learn about. Okay, when you're drawing your molecules to start with, it can be a little bit confusing, and so I have a few guiding principles to get you started. First of all, when you are sticking atoms together, you want to start with the atom with the most single electrons in the middle, and then leave the atoms with least, or usually one electron for the end. So we have NH3 here. Nitrogen has 5 valence electrons, and we can see there's 3 of them that are single available to bond. Hydrogen only has 1, so we're going to put the nitrogen in the middle. There it is, nitrogen in the middle. And so now we're going to line up these hydrogens to make covalent bonds with each of those single electrons. So you can show that. And there's another one over here. And you can move that electron around so that it's like directly across from where it's going to bond. And you'll end up with 3 bonds, 3 hydrogens on the 1 nitrogen, and you'll be done. To do this as a stick diagram, you just replace those circled electrons with a line, and it's a little cleaner to do it that way. Okay, this next molecule has 3 atoms in it. We've got the hydrogen with 1 electron to share. We've got carbon, which has 4, and we got oxygen, which has 6 valence electrons and only 2 to share. So of the 3, carbon wins. It's got the most to share. We're going to put that in the middle. 1, 2, 3, 4. We're going to leave this hydrogen to the end because it only has 1, and we're going to put on this oxygen. So oxygen could make 1 or 2 bonds. Now if we make 1 bond with the carbon, that means we got 1, 2, 3, 4 single spots that need to be filled. And we only have 2 hydrogens to fill the rest of those spots. So it makes sense to double bond the oxygen and then put the hydrogens on the remaining places. So you have to do a little bit of logic work like that. It's like a little puzzle to figure out how best to make sure that all the single electrons are bonded and you don't have any left over using the elements that you have. Now if you wanted to draw this as a stick diagram, you could clean it up, put a double line for your double bond, show some of those extra electrons there. You can draw your hydrogens. You don't even have to be directly like 90 degrees to each other. You can spread them out if you like. All right, some things to avoid when you are making your molecules. It may, on paper, be possible to make molecules that look like triangles or boxes, but because of the way that bonds sort of repel each other, those don't actually exist in real life, and so you should avoid making those because it won't be accurate. And the other thing that doesn't happen in real life is that oxygens tend not to make chains with each other. So if you got 2 oxygens, make sure you don't bond them to each other because you won't find that in reality either. Okay, so let's do a couple of these and we'll make some mistakes and then correct them. So I have 3 carbons here and I have 6 hydrogens. So I see that, of course, carbon has a lot more to bond than hydrogen. It's got 4. So we're going to do all the carbons first. Now I could do carbon and then another carbon, and then I could do a 3rd carbon down here. And then I could say I'm bonding here, and then I'm bonding here, and then I'm bonding here. Yay! But this would be making a triangle, which, nice as it looks on paper, can't really happen in reality. These electrons here would repel these electrons here, and these type of structures are just very unstable and never really exist in reality. And so we're not going to draw any of those, and so no triangles and no boxes, and so ixnay to this structure. So another possibility here, if I take my 3 carbons and I want to bond them together, is to make them into a little chain. And then I've got them stuck together by single electrons that are close. Now, how many available spots do I have for hydrogen here? Well, it looks like I got 1, 2, 3, 4, 5, 6, 7, 8 spots. And I only have 6 hydrogens. So that means that I have to use up 2 of those spots without using hydrogens. And again, a double bond is a good way to do that. So if I double bond those 2, then I can take care of 2 of those electrons and use the hydrogens for the other 6 spots. Now, a common problem that I've seen, or mistake that I've seen beginner molecule builders do, is they'll take 2 electrons that are on the same atom and they'll say, that's my double bond. But you can't do that because it's not a bond unless it goes to another atom. Okay, so now we can put on the rest of the hydrogens to take up the remaining places. And you'll end up having a nice, complete grouping. Each hydrogen ends up with 2, each carbon ends up with 8. So this is an acceptable structure for that formula. And then if you wanted to make it stick formula to make it a little cleaner, just put sticks in for each of those circled dots. Again, if you don't do this at the beginning, that's fine. It takes a while to get used to where the sticks will go and how many you can have. Okay, let's have a look at our next grouping here. So again, we've got carbons and hydrogens and also oxygens. Oxygens, if you recall, have 6 valence electrons, 2 to share, which means we're going to start with the carbons first. So we'll take our carbons, put them down. 1, 2, great. We're going to bond those together. We could put an oxygen here and bond it here and here. Well, that would be a bad idea. Why would we not do that? Correct, we would not do that because that's a triangle. We do not want triangles. Okay, so we could take an oxygen here. Great, we'll bond it. Awesome. And I will put the extra electrons on there. And what if we put another oxygen here and bond it? Awesome, we'll just keep chaining the oxygen. What do you say? Don't make chains of oxygens. You're right. Okay, sorry, I have to back up again. Don't do that. No chains of oxygens. Okay, fine. So I'm going to put 1 oxygen on there. That's fine, isn't it? Yeah, okay, fine. Put 1 oxygen here, and we'll bond that like so. And then we'll put a second oxygen here and bond it. Great, so that takes care of it. So I can't put another oxygen here. Oh, I guess I could, but then I would run out of space. Like if I put another oxygen here, and then I know I have to put a hydrogen down here. And now I got 1 hydrogen and all these spots left. So that's not a good idea as well. Okay, so let's get rid of that. What else can we put there? We can put a hydrogen there. Put a hydrogen here. Great, it takes care of all of them there. And so now I still got 1 more oxygen and 1 more hydrogen left. We're just going to do the same thing on the other side. We'll bond the oxygen with a double bond. And another one here. And then we'll put another hydrogen down here. And yay, puzzle solved. Great. So you can see there's lots of little dead ends you might take when you're first starting this. It'll take you a little while to learn all the little rules. It's kind of like any other game you might play where you'll occasionally stumble against some rules that won't work, and eventually you'll figure out how to come up with structures that do work. And of course, to make this a little cleaner, you can do this with the sticks, and you can make it look a little nicer. And once you're finished, it should have a structure something like that. Okay, I hope you learned lots about molecules today. Get lots of practice drawing your molecules and showing those covalent bonds, and we'll see you soon.